All right, welcome to calculus. So we're going to look at how to do improper integrals today. So I have this improper integral. We're going from 1 to 5 of 1 over x minus 4 dx. Now, improper integrals can come in different forms, but one of the biggest or the defining aspect of this is that we're looking for the event or the outcome where there's just some quantity of some sort that we're really difficult with being able to determine. For instance, the idea here is that we're finding the area between the curve and the x-axis. So if we're going from 1 to 5, so we're starting here at the value of 1, okay, right there, and we're going to 5, which is right there, okay. If we're going to that distance, there happens to be a asymptote right there at x equal to 4. Well, if there's an asymptote there, that means that we're following all this area right here, all the way up to that spot, and then we're flipping over to here. Now, we could do this integration quite easily from 1 to 3, but going from 1 to 5 creates this problem where we're actually switching from one spot to the other. So the first idea would be to go from 1 to 4 of 1 over x minus 4 dx, and then add that to the integration. Of course, we need the absolute value of both of these, right? Do the integration from 4 to 5 of 1 over x minus 4 dx. Now, the issue with this one is that this place where we hit 4, we add up all the area. Well, how much area are we talking about that's happening right there? Well, if we think about what's happening really close to 4, all right, what's happening, let's just say we're talking about the limit as x goes to 4 from the left of 1 over x minus 4. That is going to be negative infinity. If we look at this limit as x goes to 4 from the other side, from the right, that's going to be positive infinity. Now, if we're talking about an overall limit, of course, the limit doesn't exist here, but that's not really what we're concerned with in this instance. The thing I'm concerned with is the fact that we have this infinite value. Remember what we were doing with integration was we were essentially finding all the heights and we were adding all the heights together to get the area. One of the heights is infinite, which means that this area is infinite, which doesn't make a whole lot of sense. So it's an infinite area. So the area doesn't actually go to any one spot. So what we would say here is that we can't actually do this process here. This is not an integration we can do. This makes this integration improper. Now, there are some things that we can do in certain situations that allow us to be able to do other processes. All right, so let's just talk about a different one. Let's talk about the integration from 1 to infinity of 1 over x. Now, I know what some of you are thinking. You're thinking, well, we're going to infinity, so this is going to be impossible again. These are both improper integrals that we're looking at here, but the first one I showed you that was on a definite set of values was impossible for us to do. The actual integration gives us an infinite value, which is not something we can deal with. But here, in this one, we can actually rewrite this. We can do the limit as n goes to infinity. You can use any variable you want to there, right there at n, as 1 to n of 1 over x dx. Now, what you got to remember on this one is that this graph looks like this on the side that we are concerned with. Now, it does the exact opposite on the other side, all right? That's an absolutely wonderful drawing. I'm sure it's the best drawing of 1 over x you've ever seen in your life, right? So we're starting right here at 1, and we're finding this area, and we're going here, and we're going there, and we're going there. And what's going to happen is eventually these values, these heights that we're going off to infinity with, are going to get so small that we can actually count them all. And this is kind of neat. So this is the way that we deal with improper integrals, right? And we can go back and use this same mentality to deal with the previous example as well and show that it still gives us infinite values there. But here what I'm going to do is just go ahead and do that integration. So we're doing the limit as n goes to infinity of this. Well, that is going to be, you got to think of this right here. Remember, think of this as x to the negative 1. Helps out quite a bit if you think of it that way. So you add 1 to the exponent, right? Because we're doing integration, which gives us x to the 0. Oh, well, that doesn't work, does it? So we can't do that. So that means this is going to be turning into ln of x when we do this integration. So this is ln of x from 1 to n, right? So that means you're doing the limit as n goes to infinity of ln of n minus ln of 1. All right? So then we stick in infinity there. We're doing ln of infinity minus ln of 1. Well, I don't know if you have your calculator handy, but you might be able to do that. You can definitely do ln of 1, right? ln of 1, of course, is 0, right? So we have something minus 0. What's ln of infinity? Well, ln of infinity would, what does that look like? If you want to, you can very quickly and easily get an idea of what that's doing just simply by looking at the graph of this. So you can graph it real quick, and you can see that it gets bigger and bigger. So the graph of ln of x looks something like this. Again, a marvelous drawing, right? So when we do that particular graph there, we can see that this gets bigger and bigger, which means this is going off to infinity, which means this overall limit again is going to infinity. Well, what does that mean? Well, it means that this integration, once again, is this would be a value, or you can say that does not exist. There are all sorts of things we could say here, but ultimately the idea is that we can't find the area. There's an infinite amount of area under there. Well, is there a situation where this does work? Well, let's do one very small change. Let's go from 1 to infinity of 1 over x squared. All right, and when we do this, again, I'm going to do two switches. I'm first going to make this the limit as n goes to infinity, the integration from 1 to n, and I'm going to think of this as x to the negative 2. Now, this may not seem like it makes a big deal, but it does. And when you get to series and sequences, you'll actually see that there's a whole other aspect of this. This is what we'd call a geometric series. In this particular instance, it would be, we could look at this in a whole nother light. Not geometric series, I'm sorry, anyway, skip that. The idea is that when we do this, we will end up with something that we can actually deal with, something we can find the value of, because it's going to be decaying fast enough. It's actually going to be converging to a particular value at this point. This does actually converge here. So when we do that process, we add 1 to the next exponent, so that gives us negative x to the negative 1, evaluated from 1 to n, right? So that means that we can then do first fundamental theorem of calculus there, and we end up with negative n. We can go ahead and write that as 1 over n if that helps, right? And I'll get rid of that little piece right there. And then minus negative 1 over 1, right? And now when we plug in infinity, we end up with negative 1 over infinity, which that's kind of messy. We'll talk about it here in a second. And then plus 1. Well, the idea of 1 over infinity, that's actually an indeterminate case. Now, we can very easily see, well, that means this is going to 0. This is going, 1 is going to 1. So this is going to 1 here. You can also think about, if it's an indeterminate case, you can do L'Hopital's rule, in which case you get 0 over 1, which is just, again, 0. So there, that works as well. So either way, we end up with 1. So what happens here is that this improper integral gives us a value of 1. Now, what the things that's happening here is it still has that same shape as the previous example, but now this space right here is getting small enough, fast enough, so that it's actually converging to a particular sum, as opposed to the example previous here where it wasn't converging fast enough. And that word fast enough is actually kind of a weird thing because it's so arbitrary. And yes, it is absolutely arbitrary, but it just has to happen fast enough. And this power of 1 right here versus the power of 2 is just enough to make it change at the right speed. And then of course you had this one up here, which was an issue because we had this big jump. So when we have improper integrals, we have 3 situations that we really need to deal with. One is where we have a gap or an asymptote inside the interval, in which case there's not a whole lot we can do, especially when the limit for that individual, when we have that gap there, in this case the asymptote, when we have that piece there, we can't find the sum because we have an infinite amount of space in there because we're integrating. In this case, we'd be integrating an infinite height, which doesn't make a whole lot of sense to us. We can't do an integration for an infinite height, which means our sum, our area would be an infinite. The second scenario is when we have a we have an infinite amount of space, and the sum is infinite. So again, up here we had a finite amount of space, but the sum was infinite. Here we have a infinite amount of space, and the sum is infinite. And the last version of this is where we have an infinite amount of space, and the sum is finite. So there's three different scenarios of what we can deal with. All three of these are improper integrals, and every single time the idea is that we're switching from it being an integration with that gap in there into dealing with the limits. And we could have done a similar process up here with this one, where we could have switched this to go from 1 to 4 and 4 to 5. And in both cases, we could have again done the limit as n goes to 4 from the integration from 1 to 4. And then over here, we would have done the same thing, the limit as n goes to 4 from n to 5. And we would have done that in both situations. And what we would have found in both situations is that we would have been going from, we would have been adding the 4 in there. Actually, I'm sorry, not 4 right there, n right there in that first one. We would have been putting infinity in both of those. And since we're doing the absolute value in both cases, we would have been adding infinity to infinity, and it would have given us infinity. But you can also think of this a little bit differently, since we have the asymptote of thinking about we were doing infinite height. I hope this was helpful and useful. Reach out with questions and comments as you have them. Take care.